All right. So this is the third time I've gone to record this stupid video. I was really excited about this video, and I still am a little bit, but it's starting to be too much. So here we go. Recording. Audio is verified to be working. It's a little hot right now, so let me turn it down a smidge. And then, well, that's fine. I blew out your eardrums. That's fine. It's okay. Don't worry. They have surgery for that now, probably, or something. I'm excited about this lesson because we're going back to high school, and at its core, and also there's some theorems in here that kind of make me excited because it's like mind blowing that it's always true. We'll get to that. Let's dive in. Maybe I'll be less rambly in this one. Maybe it's ultimately for your benefit. We shall see. So our first theorem we're going to talk about is the triangle proportionality theorem. If a line is parallel to one side of a triangle and intersects the other two sides, then it divides the sides into segments of proportional length. That's pretty cool. This one's less mind-blowing, but this one, I took the time to highlight the ones we're talking about so they compare, because as I've said several times at this point, the trick, if there is a trick, the only tricky bit to similar figures, really, if you know how to solve proportions and stuff, which hopefully you do at this point, is making sure you have the right thing going with the right other thing, right? Because that's where we get tricky. So I highlighted it here in color to make it even clearer. So they're on the same side. So this AB, this guy goes to BC, equals this big one to this little one over here. It's not always big and leg. This big and leg. This theorem, it's worth noting because we're going to see a theorem that has more specific type of segments. But this is true for any segment anywhere along here. If this is parallel, if this is parallel to that, then its segments are also proportional, right? It's true for any segments anywhere in the triangle, anywhere, right? We're going to get, like I said, we're going to learn a more specific type of segment here in a couple minutes, but this is true. Let's do an example to kind of cement this in our brain a little bit, put a little concreteness on it. In triangle PQR, so this bigger triangle, BQR, ST is parallel to RQ. It's also explicitly written right here, right? Easy peasy. If PT equals, the measure of PT equals 7.5. So I'm going to go through and kind of label as I go. It's just going to be more efficient that way. So PT is 7.5. And the measure of TQ, so that's this guy on that same side, is 3. And SR, so that's this one, is 2.5. The measure of PS equals, we don't know, right? So let's set up a proportion because we just learned that these are proportional, right? So the proportion we can set up is X, or I'm going to go ahead and label it as the measure of PS just because we're going back to high school, so we use that kind of more formal notation, right? Equals ES to 2.5 equals. So we went this long side to this small side. So we're going to do the same thing over here. This long side to this small side. So 7.5 to 3. Then, just like solving any proportion, we're going to cross multiply, right? So 3 times the measure of PS is, in fact, 3 times the measure of PS. I know it's confusing and complicated and all that. But, there it is. 2.5 times 7.5. And since I did this before, it's all still sitting in my calculator. Stupid technology. So it's 18.75. Then we're going to divide both sides by 3. So the measure of PS equals 6.25. That's no big deal. Let's learn a couple other theorems and definitions and things. Keep going. So the converse, could be expected, the converse of the triangle proportionality theorem is also true, that if a line intersects two sides of a triangle and separates the sides into proportional corresponding segments, then the line is parallel to the third side. So this could come in handy if we were trying to prove lines are parallel, right? Or if we needed that information to prove something was a parallelogram or any other place. This particular theorem is more going to be useful in proofs and such, right? Because we can, if we can prove that these are proportional through a little algebra probably, then it's like, okay, these lines are parallel. Great. Moving on. Mid-segment of a triangle. This is just a definition, right? So what is a mid-segment? So before I read this, it's important to note that a mid-segment shouldn't be confused with a median, right? We learned a few units ago about medians. Medians, remember, they connected the vertex to the midpoint of the opposite side. So that's a median. This is a mid-segment, right? So we're talking about two different things. So a mid-segment of a triangle is a segment with endpoints that are the endpoints of two sides of the triangle. So like this guy between this midpoint and that midpoint, he's a mid-segment, and this is a mid-segment, and this is a mid-segment. So it connects the midpoints of the I was about to say opposite, but that's not really right. Of another side, any other side, right? So this next one is kind of where we hit. This is kind of cool, in my opinion, and it's cool that it's always true. And I'm going to spend half a second talking about this and yammering away about it because I think it's cool and I think it's relevant for our brains at this point in a geometry course to kind of go back to our roots of what geometry is all about. So triangle mid-segment theorem says a mid-segment of a triangle, so that last thing we learned at, is parallel to one side of the triangle. Always. It is parallel. Not if this is true, then this is also true. But a mid-segment is always parallel to one of the sides. That's just like crazy. And not only that, and its length is half the length of that side. So this is always, if it's a mid-segment, half the length of the other side. And that's true. That's true if we're doing triangles, a triangle that looks like this. It's true if we're doing a triangle that looks like this. It's true if we're doing a triangle that looks like this. Any type of triangle that we draw, this is always true. If we draw it now, this I'm going to draw not quite as well because I'm eyeballing it. But if we have a mid-segment, it's always parallel. It's always parallel to another side. So this, if assuming this that I drew in sketch is a mid-segment, this is parallel and it's half the length of that always. Period. And this is where I think. At this point, we've done a lot of things and learned a lot of things. So we're kind of taking a step back at what we're doing, why we're doing, right? And we even took a step back and went into middle school, which is why I'm taking a second now to say these words, because I think it's important to contextualize what we're doing and why we're learning it. And this is fundamentally different than the scientific method, right? The scientific method, we have this method of proof, and we're trying this method of proof, but the proof is different in scientific method. Scientific method, we take an educated guess. That's a horrible description of a hypothesis, but whatever. We take a guess based on known, observable, quantifiable data, information, things happening, whatever, right? And then we make a hypothesis about that. Then we test it. And then we do more testing, keep testing. And we test it from different angles. And we keep doing it. We keep running experiments. And then in a modern peer-reviewed scientific method, you hand what you found to some other people. And they try to replicate what you did. And we keep testing and testing and testing and doing this over and over and over again. And eventually we're like, okay, it's good enough. And so now it's upgraded to a theory and whatever else and all these things. And I'm really oversimplifying, but to make the point, in proof, in mathematical proof, we're doing something totally different in a lot of ways. Instead of having to run this experiment. So in order to prove the triangle mid-segment theorem, nobody sat and tried a whole bunch of triangles and just got the ruler out and kept trying it and trying it. There are infinitely many types of triangles. This would to prove it that way would be exhaustive and ridiculous. But mathematical proof that you're learning, at least a piece of, is we're taking things that are known to be true, simple, undefined terms, and we're building on. If this is true, then this is also true. If this is true, then that's also true. If this is true, and we build this up, and that's if we were to write a proof for this mid-segment theorem, which you could do at this point, but we're saying that this is always true because it builds on these layers of knowledge that have come before. And because these are true, it comes up to where this is always true. And so instead of taking the time to have to test thousands of triangles to prove it, we prove it because of this being true and that being true and this being true. So we're walking down. And as I've said in class, I don't know that I've said on video very much, but as I've said in class several times recently, when people have asked various questions or the same question repeated, why do we do these things? Or more specifically, what is math? Because I often make the statement in my class, sort of bold claim that what we're learning isn't even really math. Real mathematicians are doing something different. So people will, of course, ask the follow-up question, what is real math? Well, real math, most branches of real math, pretty much all branches of real math, some, in a very oversimplified manner, are taking a whole bunch of data and a whole bunch of ideas and trying to condense it into a universal theory of life, the universe, and everything. I'm kind of making things all very simple and slightly comical, but that's what we're doing. We're taking all this data and trying to make something, a rule that does always work. And so getting back to this, and we're going to the rest of the math part of this won't take very long, so don't stress. We're only 11 minutes in. You're going to be fine. Getting back to this, people through working out mathematical proof, just like what you've been doing, or at least some version of that, we're able to walk down looking at this theorem and then this theorem and this postulate and this thing and do these things that are true. They were able to come up with the fact that this is always true, whether the triangle looks like this or like this or like this or any triangle, this is always true. And the fact that this is always true is sort of mind-blowing. Is you mean to tell me if you draw a mid-segment, it's always a half the length the other side and always parallel? I mean, think about the relations to how this principle could be used in engineering, could be used in construction, could be used in all kinds of things. Just this fact alone lets us do all kinds of things. So in math, we're building tools that get to be applied in all kinds of situations. And I think that's cool. And so I took 2 or 3 minutes to tell you so, because we're going back to high school and I'm excited. Let's wrap up the last of what we're doing with an example. So here's an example. In the figure, X, Y, and XZ, so X, Y, and XZ are mid-segments of RST. So that's this big triangle, right? Find the measure of XZ and the measure of ST, which is this long one here. Excuse me. And the measure of angle RY X. So that's this guy right there. So we'll kind of walk these through one piece at a time. So XZ, where is XZ? So that is right here. XZ. Last time, I think was it the last video where I went nuts and kept trying to highlight the correct thing and kept highlighting the wrong thing? Was that last video? Let me know in the comments. Or was that 2 videos ago? So that's what we're looking for. So this, it says, is a mid-segment. Now, I may have drawn it wrong. Who knows? But because we said it, we can say other things, right? So it is a mid-segment. So what does that tell us? That tells us that it is parallel to another side. Great. It also tells us that it's half the length of the big one. So it's half the length of 13, which is 6.5. The measure of segment XZ equals 6.5. Wow. That's it. Wow. Wow. That's crazy. Super easy. Barely an inconvenience. Drop a comment. Where's that from? You probably know. One of the best YouTubers on the planet. Don't know him from Adam. Whatever else. So ST. So that is this one. Right? That one right there. ST. So we know that XY is a mid-segment. So that means it's half the length of this. So the measure of ST is double the length of that. So the measure of ST equals double 7, so it's 14. Wow. Isn't math fun? I'm telling you, math is fun. If you think otherwise, you are incorrect, sir. Math definitely can be fun because it's cool, because it always works, because it takes a whole lot of chaos and makes order out of it. It's pretty awesome. The measure of RYX. This one's probably going to be slightly less obvious, right? So the measure of RYX, let's find where that is. So RYX, so that's this angle right there. That's the one we're looking for. Okay, so how can we find that? Well, the only other angle measure listed is 124 degrees. So there's a few different ways to look at this and to think about what it is, right? There's one like really straightforward one, which I'll illustrate first, and then I'll show you that even if you didn't see that, maybe you saw something else. And this is another reason why high school geometry is cool, because at this point you have so many tools in your tool belt and so many different ways to be like, oh yeah, this is totally true because that, and whatever else. It's fun. It's cool. Okay. So first of all, these lines we know because they are mid segments. These lines right here are parallel, right? Both of these, yeah, are parallel. I've already marked that in yellow, but these two are parallel. So that, if we look at this transversal that is crossing it, close enough. You get the idea. This guy, if this is a transversal and we're looking at this one and this one, what are those? Those are alternate interior. They're congruent, which means that without even doing any math, just by doing any math, doing any algebra, doing any arithmetic, really, we can just say that the measure of angle RYX equals 124 degrees. There you go, right? That's easy peasy. So that's great. Now, just continue connecting the dots, because I think it's important for you to be able to see things. If this is parallel, we also know, because this is a mid-segment, that it's parallel to this one, right? We know that's true. So what shape is this? This shape is a parallelogram, because it's got two pairs of parallel sides, which means this one's 124, which means this one is supplementary, so it's 180 minus 124, so it's what, 56, right? And then these are linear pairs, so 180 minus 56 is 124. So all of those different ways and things, it's 124 is the answer. But the cool thing is all the cool ways you can get there, and how all these different pieces connect. It's fun. It's good. It's great. Another theorem that is proportional parts of parallel lines. And it says if three or more parallel lines intersect two transversals, then they cut off the transversals proportionally, right? So let's get our thing with some opacity in it. AB is proportional to BC. All right? So that is what is going on here. It's kind of, this is actually in the book that we're using in my class to do homework and stuff, they call this a corollary to the triangle proportionality theorem. It is, because you can kind of imagine that in like this one specifically, like if we keep on drawing this out, this is eventually forms a triangle, right? So that's a corollary, remember, is a theorem that builds on another theorem. And so that's why this is connected with the other thing, is because this is just kind of goes with the other thing. And so that's why this works. So it's the same sort of proportionality in this. And so EF goes with FG, right? And so that's the connections here. So if we have two transversals cutting three or more parallel lines, then these sides are proportional. It's great. There's one more theorem and then a quick example, and then we're done, right? So congruent parts of parallel lines. This is also cool. So if three or more lines are cut off congruent segments on one transversal, so we've got that labeled here. So if these are congruent, right, then they cut off congruent segments on every other transversal to these three parallel lines. This is also kind of a mind-blowing sort of a thing. What this tells us is that since these are congruent, so this is congruent to that means that with this other transversal, they're also congruent. And that is true for every single transversal we could possibly draw on this thing, right? So we draw like this super steep transversal. So because we know these are congruent, then these would also be congruent, right? Any transversal we draw on this, because we know one set is congruent, any other set, so no matter how stretched or how whatever, it always works. And that's the cool thing about math theorems is it lets us say so much with so little. It's just fun at this point. Let's do a quick example. This one won't take very long. So find x and y. X is up here and y is down here. So we have 3 parallel lines. We know they're parallel lines because it's labeled that they're parallel lines. They're cut by 1 and 2 transversals. We're also told explicitly, because it's written on here, that this is congruent to that. Because of what we just learned, that means that every transversal cuts congruent segments. So this is congruent to this because it says so, and this is congruent to that because of the theorem we just learned. Easy peasy, lemon squeezy. So the algebra on this is going to be really easy, right? This is congruent to that, so we just set up a little equals equation. So 3y plus 8 equals 5y minus 7. That's an easy thing to solve. We're just going to subtract 3y from both sides. And then we can also subtract 8 from both sides. This one cancels and this one cancels. Why did I do that? I have no idea why I did it that way. Got excited. So everything canceled on this side. We end up with 0 equals 2y minus 15. It's acceptable. I accidentally added an extra step. Not a big deal. It does work. Probably just as well that we did this, because sometimes people will do something like this and they'll freak out because they forget 0 is a number. And so it's probably just as well that I accidentally made that mistake. It's not really a mistake, but so we're adding 15 to both sides. So we get 15 equals 2y. And then we've got to get rid of that 2. So we're going to divide by 2 on both sides. So we end up with y equals 7.5 or 7.5. You could write that either way. All right, to find x, it's pretty much the same. Honestly, it's not that big a deal at all. Pretty much the same thing, because we know that this is congruent to that, so we can set up the exact same kind of equation. So 6x minus 5 equals 4x plus 5. That's easy to solve. Let's see if I can do it without adding extra work. Minus 4x. And then plus 5. I think I did it. We'll see. So this cancels and that cancels. Looking promising so far. 6x minus 4x is 2x. Equals 5 plus 5. That's easy peasy. Equals that. Now divide by 2 on both sides. We end up with x equals 5. And that's it. That's it for that lesson. It's, yeah. Anyway, the math is easy. Math was pretty easy. We're coming back to doing things. So it's a good point in kind of the slightly more than halfway through the course time to be like, this is why we're doing what we're doing again. And so hope you're having fun. I certainly am. We will see you in the next one. If you're one of my students, do your homework for Pete's sake. See y'all later. Bye-bye.